Hello. In this video, we will discuss momentum, conservation of momentum, and the center of mass frame. We will then solve a problem demonstrating the use of conservation of momentum. Momentum is mass times velocity. It is a vector quantity with the same direction as the velocity. When is momentum conserved? When there are no external forces on the system. Note that momentum is conserved for each perpendicular axis independently. Remember to include the momentum of all objects in the system. You can choose the system such that any interaction with anything outside the system can be described by simple forces. Conservation of momentum is particularly important to the analysis of collisions. To fully understand a collision, we also often want to consider if kinetic energy is conserved. Kinetic energy is conserved in elastic collisions. Elastic collisions tend to involve objects bouncing off each other. A completely inelastic collision occurs when two objects collide and stick together. For an inelastic collision, the most amount of energy that can be lost in a collision is lost. Related to momentum is the center of mass frame. A closed system is a system with no external forces. For a closed system of particles, the total momentum of the system remains constant. So, the system as a whole has a certain momentum. We extend this idea by defining the center of a system of particles which is attributed that momentum. Suppose we have a system of particles, each with a mass, position, and velocity. The total momentum is the sum of the momentums of each of the particles, mv. We can multiply and divide by m, the total mass, to represent this in terms of an average velocity. If we want to think of this average velocity as the velocity of the center, we need to specify where the center of mass is located. The center of mass position is the same weighted average of the positions of all of the particles. The center has the same velocity as the weighted average we calculated earlier. Thus, we can think of the whole system of particles as having a center r, which moves with the average velocity of the system. We further define the acceleration of the center of mass as the derivative of the center of mass velocity. Note that this is also the same weighted average of the accelerations of each of the particles. You can look at any system of particles as a single object located at the center of mass with mass equal to the total mass of the system and position and velocity as described earlier. This means that if you treat the center of mass as a particle, then any external forces on the system can be considered a force on the center of mass. This means that the total force, which is equal to the sum of the forces, is equal to the total mass times the center of mass acceleration. Note that the total force must include the forces on all of the particles in the system. The center of mass defines a new reference frame for the system, which we usually denote with primed coordinates. The position relative to the center of mass is the position of the particle minus the center of mass. The velocity is equal to the velocity of the particle minus the center of mass velocity, and similarly for the acceleration. The total momentum of the system when measured relative to the center of mass is 0, as shown here. We add each of the velocities relative to the center of mass, we expand that relative to our original coordinates, we can then separate each of these terms, and we get the total momentum minus the total momentum, which is 0. Center of mass is what allows us to apply Newtonian dynamics to rigid bodies and non-point-like objects and systems. Now we will consider a problem which can be solved using conservation of momentum. Alice, with mass ma, and Bob, with mass mb, are standing on a frozen lake, which will have static and kinetic friction coefficients 0. Alice throws a ball of mass m to Bob with velocity v relative to the lake at an angle theta. Is that in focus? Bob catches the ball and throws it back to Alice with the same velocity v relative to the lake and the same angle, theta. What velocity is Bob moving at after releasing the ball? We do not have any information about the forces involved in throwing and catching the ball here, so we should probably use momentum to solve this problem. We do not care what happens to Alice in the end. Sorry, Alice. So our system will consist of Bob and the ball, after the ball has been released by Alice. We will choose a coordinate system with z in the vertical direction and x parallel to the lake, with positive x pointing from Alice to Bob. The total momentum of our system is P total equals P ball plus P Bob. Initially, the momentum of Bob is 0, since Bob is not moving. The initial momentum of the ball is P ball initial equals mv. At this point, we notice that there are forces acting on the system, namely there is a gravitational force acting on both Bob and the ball, and a normal force between the ice and Bob. Fortunately, momentum along each axis is conserved independently. We know that Bob is going to stay standing on the ice, so the final velocity of Bob in the z direction is 0. Thus, we will only consider the momentum in the x direction. Bob's initial momentum in the x direction is still 0. The ball's initial momentum in the x direction is mv cosine theta, since Alice throws the ball with some upwards velocity. Thus, the total momentum is simply mv cosine theta, and this will not change because there are no forces acting along the x-axis. After catching the ball, Bob tosses it back in the minus x direction with velocity v cosine theta along the x-axis. Thus, the final momentum of the ball is p ball final equals negative mv cosine theta. So, since momentum is conserved, our initial momentum must be equal to our final momentum. Our final momentum is going to be p ball final plus some momentum for Bob. So our initial momentum, mv cosine theta, equals p ball final plus p Bob final equals negative mv cosine theta plus p Bob final. And then rearranging this, we get p Bob final equals 2 mv cosine theta. Then we want to find the velocity of Bob. So the momentum of Bob is equal to mass Bob times velocity Bob. So the velocity of Bob is 2m over mv v cosine theta. And that is our answer. So to recap, the momentum is P equals mv. Momentum is conserved for each perpendicular axis independently when there are no forces along that axis. We also discussed the center of mass frame. The center of mass is given by this weighted average of the positions of each of the particles in the system, where m is the total mass, the sum of the other masses. There is also a center of mass velocity, which is both the derivative of the center of mass position and the weighted average of the velocities of each particle, and the center of mass acceleration, which is both the derivative of the center of mass velocity and the weighted average of the accelerations of the particles in the system. We also note that F equals ma holds for the entire system, where F is the sum of all forces acting on the system, m is the total mass of the system, and a is the center of mass acceleration of the system.